Last time I did the class, we had some issues with Alma forgetting her pen, and then the tablet not having a wide span. But I did cover two sections, and today we're going to review a little bit just to make sure we understand the key points to concavity. And when I looked at the homework, I think I have only one real problem where concavity is actually asked for. On the exam, you will be asked only what is the inflection point. And as to concave up and concave down, there's only going to be one problem of that. But that again goes with the test to if it's greater than 0 or less than 0. Anytime we have that condition, we know that the concavity is associated with that. So let's talk about concavity. The second derivative of a function, if we set f double prime of x equal to 0, we find value of the inflection point. Once we have that, then we go to the original function. F of that x value will give us the y value. So that we have an xy that is the inflection point. Then we said we've been using tables for all of the min-maxes, and if we had this, we would have our inflection point separate. We're going to just say it's negative infinity. It's never more than that, because I only asked that for a cubic. We would test it to see if the behavior is positive or negative, to know if the concavity exists. The inflection point is that one point as x is moving, because it's in a moving, it's not monotonic, it is a moving function. It is that point where it pauses and starts the change to another direction. And it's not even visible because it's a continuous function to that inflection point. So we did that. And today we're going to talk about something that is so wonderful and so easy and a great break in what we do. And that is looking at the existence of limits. And the book is fantastic about stating, because I got this example here, where we took limits in chapter 2, and we started them in chapter 3 just to explain derivative. And in doing so, we came up with some quantities here where we understood the limit of some of these items. Because we simplify, we could get to 0, and that's a rational expression. And on this one, we have infinity. On the next one, we have 1 because it's an identity process. Good to see you. I don't know where your compadre is, but I mean, I know. And then, of course, the ones that work out easily. And limit, analyze, and then state where the limit is going and make a determination. Infinity is not a specific limit, but it tells us it is progressing in a motion. And so, therefore, it is referenceable. Okay, well, what happens when we get the limit approaching 0 in a denominator, in both the numerator and denominator? Well, L'Hopital attacked this problem, and he had to make a reference. If you couldn't do the algebra to remove the 0 in the denominator, remember, I gave you tools, divide by the degree of the variable on the bottom to the top and the bottom so that we could have a concrete value on the bottom. And I did that with you in chapter 2. But what if we can't? What if we have a sine function on the numerator and a polynomial in the denominator? Well, there's no way we can do it because we create the same process of making that division happen within the function, because we have to divide by whatever the degree is in the denominator or whatever the function is in the denominator if it were a trig function. And this book, because it's new to me, the other one had more polynomials than trig. This one has more trig than polynomials. If you've noticed, have you noticed that all my homeworks have a lot of trig? Yeah, which is fantastic because, you know, you're going to get Dr. Deanna, and she, you know, you want to be prepared. So, I mean, I'm not saying it's bad. So what happens is L'Hopital said that if we take the derivative of the numerator independently of taking the derivative of the denominator, that we would have a very close solution. Is calculus ever exact? No. Because you're talking about infinitesimal decimals or giant numbers, and it would not be feasible to operate in that world. So we're going to be so close it's true. Does that make sense? Now remember, a theorem is an accepted rule that has not been what? So the theorems hold until somebody says, "Oh, he lied," you know. But of course, he was 1600s. It's I promise there's a lot of you all that are really looking into if it's true or false on these kind of projects. So what we're saying here is saying if we have a limit for the existence of 0 over 0 and undefinable and not L'Hopital's rule, and take the derivative of the independent numerator and denominator and get some general idea of what that function is doing. Am I clear? Super easy. Who wants to do the quotient rule? Oh, no. Okay, I mean, so this kind of but it's only used on limits where it's 0 over 0. Is everybody comfortable with that? Okay. Then we have another, and it's called the indeterminate form. Indeterminate is that we can't really say what the solution is, but we can come into some kind of agreement that this is true. Is everybody clear? Indeterminate form. You have to first state that this is happening in that limit and then work from there. Okay. Well, there's other forms of that indeterminate form. And now, L'Hopital used 0, 0, but it holds true for a ridiculous thing like infinity divided by infinity. Well, that's kind of ridiculous. So, you know, that's indeterminate. So is the factors of infinity times 0. So is infinity minus infinity. And you would think, well, Alma, that's 0. Well, actually, it's not. Because each function has an involvement of items that have either a different spin on itself as it moves, you know. So there is a variance there. So we're going to look at that. And I do have an example of that. All right. So we're going to lead you by the hand on the first one. And the reason is because it's a polynomial over a polynomial, and we're using as the limit as x approaches infinity. When x approaches infinity, we automatically insert it. And you remember how we did that? We just insert it in and see what happens, right? So if I did it, okay, if I substituted, I would have 5 times infinity cubed, which is mind-blowing, minus 6 times infinity. And here is that very same process that I just discussed with you. Well, which one's growing faster or quicker? The first term. Yes, the first term. So that's why I'm saying it's not zero. Well, anyway. Okay, so then on the bottom, we're going to have 7 infinity cubed plus 7. Now, in the algebra of this, okay, in the algebra of this, we would have divided the top and the bottom by what? The highest degree variable. What is it? Because in this case, we have infinity over infinity plus 7. Okay? So, in this case, we would have said, oh, well, just divide everything by x cubed, and then that will zero out. Because if we have 1 over infinity, we're approaching what value? Thank you. We're approaching 0. And that's what I taught you. Okay? That's what I taught you. I said, so we know the limit here is going to be 5/7. But L'Hopital says, well, just take the derivative and go from there and see what happens, right? So I'm going to have 15x squared minus the 6. Everybody agree? And I'm going to have 21x squared, period. Right? So in this case, we would have simplified. So we would have had 15x squared over the 21x squared minus 6 over 21x squared. If I put infinity there, this guy is what? 0, right? So we're not worried about that. Well, these cancel, and then I'm going to reduce it, right? I'm going to reduce it by 3. Well, what did we say? Exactly what we did. If I divided by x to the third in my numerator and in my denominator, I would have gotten real value. And so it's approaching some horizontal condition at 5/7. Is everybody clear? Questions? All right. Well, naturally, we're going to do one. First, we're going to test it. So if I put in 0 here, well, sine at 0 is 0, and 0 here is 0. So we're going to apply L'Hopital's. Well, one person, are you sure that's not a hospital? No. Okay, so we're going to use L'Hopital and then do the limit. Okay, let me take this bottom part off. Okay, so if I do, I'm going to have a -2 cosine of this mess. And then the chain rule says I'm going to have a value. What am I going to have? Chain rule. It's nasty. And then on the bottom, luckily, I have a number. So no matter what, I have a concrete value because we have 4 in the denominator and the top is almost immaterial, right? But we're going to do the math. So I'm going to end up with that looks like a -18t squared cosine of 3t cubed all over 4. All right. So at this point, I don't even have to do the math. What is, if I put in 0 for t, I'm done. And we would have said in using the 0 for cosine, it would have been 1, but the t would have made it 0. Is everybody comfortable with that? Questions on that? Am I clear? Okay. Tell me if I'm clear. This guy here is we're trying to find the limit as theta approaches pi halves. So if I put in pi halves here, I'm going to have 1 minus 1. And if I put pi halves here, I'm going to also have 1 because it goes to negative 1. So I'm going to have 7 minus 7. So I end up being able, so I proved that I'm going to use L'Hopital's rule. So now we're going to do the math. So in this case, I'm going to have a positive cosine theta, right? Oh, no, negative. Sorry about that. Negative. And then on the bottom, I'm going to have a negative 7 sine 2 theta. And chain rule says 2. Yeah, you were doing the math. I appreciate that. Y'all are so fast. I love it. So I'm going to have a negative and a negative. It's going to be a positive. So I'm just going to put cosine theta over 14. I know what I'm math. I do. 14 sine 2 theta. Okay, now we have to check if I insert pi halves in this guy, and sine is going to be what? No, it's 2 theta. So what is it? 0. Okay, so we have a 0 in the denominator. That means I have to go back and do it again. So we have to have a 0 here. On the top is not bad because we also have a what? Okay, so now we have to use L'Hopital's again. And that's the beauty of L'Hopital. When you get to the next class, you'll do it multiple times. In this class, I only have like a couple of problems where you do it twice. And that happens when you start doing those partial fraction business. All right, so I'm there. So I'm going to take it again. And the derivative of cosine is negative sine. All right. And derivative of sine is cosine. And then we also have the chain rule. So I'm going to clean it up again. Is that okay with everybody? Righty. And I'm not skipping any stuff. So make sure I don't drop a sign. It's going to be 28. And I'm going to insert the pi halves. And this is awesome because if I put pi halves, now I have a 1. So I have a negative 1 over, and the cosine of 2 times pi halves is pi. That's a negative 128. So my answer, my limit, is a positive 128. Questions? Oh, it's not math. I know, I show every step. Pretty disgusting. Everybody breathing? Righty then. We're going to now each of my examples are very specific. I start with something innocuous, and then I go to something that's a little more involved, and then I go to one where we have to do a little bit of reconstruction and then test it, if you will. But we're going to test this one right off the start gate. So if I put in 0, I have 5 minus 5 over 0, which is 0 over 0. So we have to use L'Hopital's rule. Okay, so I'm going to rewrite this guy first. And thank goodness we're not doing the quotient rule, right? So they've been very messy. So now what we're going to do is we're going to take the derivative, and that will give me a 1/2, and then I would have the argument 3y plus the 25 to the negative 1/2, and then the chain rule would give me an additional 3. Is that correct? Okay, good. And of course, derivative of a constant is, okay, so I'm not going to place that one. I'm just going to do that. And then on the bottom, I have a 1. Is everybody good? Everybody breathing? Alrighty. Well, what happens here? Okay, well, I'm going to clean it up. I'm going to have the 1 over 2, and this is in the, 3, sorry about that, 3 over 2, and this is the square root of 3y plus 25. Is that correct? All right, we're going to drop in our 0, and this time we have success. Because this is going to be 0 here, but that square root of 25 is 5. Looks like 3/10. What do you think? Everybody concur? Now remember, we can't use it unless we know it's 0 over 0, infinity over infinity, or infinity minus infinity. Those type of areas is where we can use L'Hopital's rule. Is everybody good? All right. Well, here's our favorite. I know it's your favorite. E to the, I always mess up on this guy because it's a power rule on top of an exponential rule. And there's many ways of dealing with this guy. Okay, but I'm going to just head on. So we're going to do this. So if I have infinity, I have e to the infinity, which is infinity, right? And then 4 times infinity of e to the infinity is also a form of infinity. We don't know the exact infinity, but we then know we can use L'Hopital's rule. Is everybody comfortable with how I'm explaining this? Because, it's not always used. Okay, so I'm going to rewrite this guy down here. And we have a product rule and chain rule. Oh, my stars, it's just crazy. Okay, we're going to do the numerator. And I'm going to have x to the 8 to x to the 8. We don't reduce it because it's e to the u is e to. Oh, I'm sorry. I forgot. Oh, I didn't do the du here. I'm glad I even said the rule. Thank you, guys. Man, like I said, always mess up somewhere on that e thing. It's the du of x to the 8. Okay, down here we have the product rule for it first. And so I'm going to have 4e to the x plus 4x e to the x. Is everybody good? We're going to test the limit. Well, I got a lot of infinity on the top, right? On the bottom, I have this is infinity, and this is infinity, isn't it? So back to the drawing board. Okay. If I did the math right. So now I have a product rule on the top. Oh, wretched. You know, we're just going to have infinity here by the time we get done, but I don't know. Maybe not. Maybe not. 8 times 7x to the 6 e x to the 8 plus 8x to the 7 e x to the 8. And I'm going to have to do that real quick. And I should have done it up there. Oh, this is so good. Oh, so good. I forgot about the factor rule. Let me erase that guy because I'm going to pull out a 4x and that'll give me what I need, I'm pretty sure. That'll give me 4e and an e. Sorry about that. And an e to the x. It's kind of like, I don't remember doing too many of doubles. That will give me 2 x to the 6 x to the 7. Bottom, I'm going to have the 4 e to the x. That'll give me a 1 plus, and that'll give me, because that's what I'm factored out. Erase that. I did not. Oh, I did take out an x. I can't take out an x. Only a 4e. Sorry about that. This stays 7. Okay, because I can only take out that. Plus a 4, an x. Yeah, I can have an x. Because this one did not have an x, because I did the 4. Yes, that's correct. All right, let's see what we have. Let me clean it up. Let me see if I see anything else that I forgot. And in this case, we can possibly divide by x and get rid, oh, this is an exponent, and it didn't look like an exponent. Sorry. We can divide by x and then get a 1 on the bottom. We can do that. Algebra is always possible. Because it's going to end up being infinity. Now we have a 1 on the bottom, and on the top we have infinity. The answer is infinity. Sorry about that, the factoring. And you know I love to factor, so I used to find all of that. And that was the last one I did. Like I said, it's not a long homework, but they're involved. You got to look at them. You have duplicates of this one and a bunch of these, a variation of this guy. And then we have some single. You'll have one with a cosine in it. And on this one, on the on the ones where you have a normal polynomial, you won't have any. They're all trig, E, and square roots. Okay, on the homework, and there's only like 9, if I'm not mistaken. Is everybody comfortable with that? Questions on this? So we have to first prove that that L'Hopital's rule is applicable. And it's an indeterminate form. So you're talking about 0 over 0, infinity over infinity, infinity minus infinity, infinity times 0. Not times 0, infinity times, 0. Okay, so we're going to do this guy right here. On optimization, we've kind of hit this because we've been taking a lot of derivatives and finding the mins and maxes, and we've been, it's a form of optimization. But on this regard, we're talking about the inclusion of either geometry or either sine curves or enclosed shapes within other shapes. All right. So this is known as applied optimization, and the solving for it is very, very important. The reading of the problem is probably the setback to this guy, because you have to look at which motion is doing what, and if you're using ratio comparisons, but drawing is the first idea given to you, besides listing what you know. Because this is Polya's 4 steps for problem solving. You read the problem for understanding, and you have to find out what the unknown you're looking for. Introduce the variables. The variables for us are complex. Sometimes we refer to them as x, y, or the other one in terms of x. So this can get a little confusing, and we're going to have delta no matter what. Somewhere in there's going to be a delta. So understanding the variable is really important. Write the equation. In this case, when we're talking about optimization, we have to know the limits of where the function exists in the parameter that we're speaking of. So that is another important aspect of optimization. And of course, we find the critical points and the endpoints of the domain to make sure that we have optimized to the request of the question. Now they state the second derivative to find if it's in line or not. The second derivative is an inflection point. And what you do with that guy once you set it to 0 is you're looking if the value of it is within the domain. If it's not, we're done. We're good. We don't have to consider any outward values. But they use it as a test. I didn't see the application of it other than applying the fact that if it is negative, then that particular inflection point is not of importance, because we're looking all at a positive area, which is above the x-axis. Does everybody come? By all means, we can do it. Here we go. A rectangle is constructed with its base on the x-axis and its upper 2 vertices on the parabola y equals 9 minus x. Okay, so the first consideration is we're understanding that we want the dimensions of the rectangle with the maximum area. So we want 3 things. We want length, width, and area. Okay, and we're given the restrictions of this. So we know on this guy, and I'm going to draw it, not to scale. So this is all we want of the parabola, all of what we want. And in here, we're sketching a rectangle, an optimum rectangle. Now it doesn't, now I drew it kind of, like it's not going to be exactly 2. Okay, so we understand another thing, that this part is the positive side. So we understand that we're going to have to double it, don't we? We know that x is doubled. The height is what it is, because those are the same as the sides. So that's the first concept of doing this particular problem. So if we start with the base, or the length, we know the length is going to be 2 of whatever the positive x is. Is everybody comfortable with that? Questions on that? All right. Well, the width, which is the y, is concerned with the function they gave us. Tells us where it goes on that first half of the parabola on the right side, and we just need the height. So this is that length of that side. Is everybody comfortable with that? Everybody good? All right. So now we're going to construct our equation. And I didn't put any real hard ones. And I did not do any in business, because there's nobody in here in business. So I didn't do any problems with business. That's a lot of E. So you know. Okay. So we know area of a rectangle is length times width. So area in terms of x is going to be my length my width. Is everybody okay with that? I'm going to do a little bit math, so when I take the derivative, I'm okay. But check my math, look, you know how I am. All right. So now I'm going to take the derivative. All right. So now that I've done that, I have to find the critical points, if any. In some cases, it can be more than one, but on this one, it's only one, because we're not dealing with it. Oops, moving it over here. I'm going to divide by that 6. And so the x is going to be plus or minus the square root of 3. Well, we don't want negative height, so we're only taking that. All right. So our next step. So we're going to do the L and the W. All right. Here we go. Well, the L is 2x, and we know x is that, so we know it's 2 square roots of 3. Is everybody good with that? Yes? Okay. Then our width is going to be 9 minus the x squared, which gives me 9 minus, what is that, 3, which comes out to be 6. So we've got the measurements of each of the parts of that rectangle, and they want the area. Well, we know that the area was length times width. So they wanted this, this, and this. Questions? Now, this is not how you need to work the problem. This is how my brain has to put it in order. Does that make sense? Any way you approach it, it's all good. I think there's 10 in this one. I'm not doing 10 problems with a team. I'm going to take a short break. Everybody needs a short break. I probably have to go get my um, sweater.